From walking your dog in the morning, to dribbling a basketball, or just simply getting chased by a very well-trained, unharmful creature that doesn't bark at all. Your body is only capable of doing this due to the presence of the nervous system and your skeletal muscles. The nervous system and the skeletal muscles allow body movement, and without these two factors, you'll probably end up like this. Even the slightest body movement requires the usage of nerves and muscles.
Yo, Acom.
These nerves and muscles work together constantly to allow you to do the little things and the bigger things in life.
Yo, Acom.
But despite that, every single body movement you perform occurs in a muscle contraction, which is the activation of tension-generating sites within muscle fibers. To put it in simpler terms, it is when your muscles become shortened and tightened. Now, muscle contractions actually consist of very fine details and complex processes and mechanisms, which happens in a matter of milliseconds. These mechanisms can be categorized as the sliding filament theory. The sliding filament theory begins in the brain, where the motor neurons send messages through the nerves of the central nervous system. During this process, acetylcholine, also known as ACH, is released from the nerve endings. ACH is released to help carry signals across a nerve synapse. Once the message has been received, the message continues down the cell body, leading to an axon terminal, which connects to a muscle fiber. A muscle fiber is covered in a transparent tubular sheath known as the sarcolemma. When the axon terminal connects to a muscle, this will trigger an action potential that will spread to the rest of the membrane, which will depolarize the T tubules. This will then trigger the release of calcium ions that is stored in the sarcoplasmic reticulum. Now, let's go deeper in the muscle fiber to locate the basic unit of a muscle tissue. This is called a sarcomere. So to fully understand this diagram, you'll have to understand what all these different bands do when a muscle contracts. So, looking at the A band, which consists of thick filaments of the protein myosin, when a muscle contracts, the A bands stay constant, meaning it is unaffected in a way. Moving on to the I bands, these I bands contain very thin filaments made of the protein actin. As the muscle contracts, the I band shortened. Similar to the I bands, the H bands also shorten as the muscle contracts. To finalize everything, Z bands or Z discs are present to mark a boundary of the sarcomere which actin filaments are attached to. Any shortening of the actin filament will result in a shortening of the sarcomere, which ultimately shortens the muscle, leading to a contraction. Now that all of that has been discussed, here is how the sliding filament theory actually works. Going back to the point of calcium ions being released, the ions attach to a protein called troponin, where then it pulls tropomyosin, which is another protein involved in the muscle contraction. The contraction begins when an ATP molecule turns into ADP with a single phosphate ion. This allows the myosin head to extend and connect to a binding site on the actin. This forms a cross bridge. An action identified as a power stroke allows the myosin to pull the actin filament towards the M line, thus shortening the sarcomere. The ADP and P is then released during the power stroke, and the myosin head remains attached to the actin filament until another ATP molecule binds on the myosin. This allows the myosin to release and go through the cycle once again. But if you're lazy like me, it relaxes and remains unattached, so no muscle contraction occurs.
Yeah, why is it all over me?
Now get out of here. Yo, Acom.
Oh!